Hello, today we'll be covering simple harmonic oscillators. A couple of things I want to point out. Oscillation, I think, is pretty simple. Think of a skateboard traveling down a ramp. It's going to go, it's going to come back, it's going to go, it's going to come back. If friction didn't exist, it'd go on forever. Why is this an oscillating machine? Well, let's consider that the skateboard encounters gravity and a normal force at some angle. Because that normal force is at an angle, it's going to have an x component. I'm going to put that in a different color. Some sort of x component. Because the angle is greater at the top, the x component of that force will be greater. Near the bottom, the x component of that force of gravity, force of normal force, would be less. And on the other side, it will be the opposite, with greater force on the top and less force towards the bottom. At the middle of the ramp, there's no force. If I were to start my skateboard right here, it wouldn't move much, or at all, because there's no force in either direction. So that's why when you're coming down a ramp, the hardest force is right at the top, but the max velocity, as you know, is in the middle, before the force of normal force starts pushing you the other way. Oscillating motion is any motion like that. We can look at a spring. A spring, if I were to just, in a frictionless world, let it go until it stops moving, it would stay put right here because the net force is 0. If I were to raise that block to right here and let go, the spring and gravity would push it down, and then eventually when the spring is stretched fully, the spring force would push up. So there's a force down and up over and over. In a frictionless environment, this gives you an oscillating motion, or a child on a swing. So what makes simple harmonic motion the way it is? What makes simple harmonic motion simple harmonic motion? The existence of a restoring force. A restoring force, all that means is the farther you travel, if we can get this out, the farther you travel, the more force there is the opposite way. Let's think of a block in this position right in the middle. If I were to leave a block here, it would not move. The block in its current position has a positive, we define this point as 0, so it has a positive displacement, so there's a positive x, but the spring would want to exert a force pulling the block to the left. So we'd call that a negative force. If the block was all the way out here, there'd be a large x displacement in the positive direction, which means there'd be a large restoring force in the opposite direction. It goes the same this way. Here we have a negative x displacement because here x is 0. So there's a negative x displacement. But at this point, the spring would want to push the block towards that 0 point. So there's positive force. So when there's negative x, positive force. When there's positive x, there's negative force. This brings us to our equation that force is inversely proportional to the displacement of x. If that's not the case, it's not simple harmonic motion, plain and simple. So again, a restoring force is simply when the block is at its center, there's no force, the spring is neither pushing nor pulling. If the string is being stretched, then the force will be opposite. Positive x displacement, so negative force. Here we have negative x displacement, so we have a positive force. A pendulum works the same way. We're going to think of a pendulum in a minimally, this angle has to remain pretty small, about 12 degrees. If it gets any longer than that, you get some funky physics, and we're not going into that today. We know that just like the skateboarder at the park, the force of gravity is straight down, but the force of tension is off at an angle. What this means is that the force of gravity In some ways it's canceled out, but the force of tension has an x component, which is why we see the ball traveling this direction. If the ball was instead over here, the force of tension would be in this direction, with force of gravity still straight down, so we have a force traveling the other way. You know when you're on a swing, the fastest you go is right in the middle. Same here. You have your max velocity right at the bottom because you have a large force pushing you, and then as you get closer you have a smaller force, a smaller force, a smaller force. But force, even though the force is smaller, force is mass times acceleration. Your mass isn't changing, so you're just accelerating more and more and more until you reach the middle. Then you're accelerating in the opposite direction. That doesn't mean you immediately start going the opposite direction, just that your velocity starts decreasing until it hits zero at the peak, and then you start traveling the other way. So a pendulum is also a simple motion, simple oscillating motion. So amplitude, what is amplitude? Well, just like amplitude happens in a sound wave, and we see amplitude as the maximum peak, amplitude in this, here we have a wave of motion between these 2 points. The amplitude is just the farthest displacement from that central location. Here we have an amplitude in the x direction. If this is the farthest point, or like where it was released from, this would be our amplitude. So time, period, frequency. Period is the time it takes to go through one complete oscillation. If you are on a swing set, this would be the time it takes to go not only there, but back. If you were a block on a spring and the spring was compressed, it'd be the time it takes for you to stretch past that 0 point to the opposite amplitude and back. And the period is the time it takes to do this. Frequency is how many oscillations can I do per unit time. A simple way of thinking about this, if the period is 2 seconds, right? In 1 second, how many oscillations will I do? Well, in 1 second, I'll do half an oscillation because 1 over 2 is half. So the frequency, we measure that in hertz, is 0.5 per second. If it took 2 seconds, let's say instead of 2 seconds, it took 1/3 a second to complete a period of oscillation. Well, 1 over 1/3 is 3. So if it took 1/3 a second to do 1, how many can we do in a full second? We can do 3, so 3 hertz. So the period is simply 1 over the frequency, and the frequency is simply 1 over the period. So, uniform circular motion and simple harmonic motion. Let's say this is a Ferris wheel traveling the same angular velocity throughout. So it took the same amount of time to complete this slice of the pie as this slice of the pie. If this ball is traveling back and forth in simple harmonic motion, just like a skateboarder, the x component of a skateboarder's ride, we know a skateboarder isn't going max speed at the top, it's going max speed at the bottom, and it's speeding up on its way down, and it's slowing down on its way up, speeding up on its way down, slowing down on its way up. A way of thinking about this, let's have this blue ball represent the y of the x displacement of this merry-go-round. Well, the x displacement of this first portion, let's say it takes 1 second to complete this slice of the pie and 1 second to complete this slice of the pie. The x component of this slice is very small, just like in simple harmonic motion at the top of that skateboard or that pendulum. When that pendulum is just released, that x component is very small. But in this slice, the x component is quite large. So it'll take 1 second for the ball to go from here to here, but also 1 second to go here to here. So let's say in this example, the periods were the same. It took 1 second for this red ball to complete one full circle, and it took 1 second for the blue ball to go there and back. What's really cool about this, let's say we had a light fixture that shined light straight down throughout. If these balls stayed with the same period, started at the same x position at the same time, the shadow, when the red ball was here, the shadow of the red ball would always be cast on the blue ball, and so forth and so forth. That pretty much just, that equation just goes over what we just talked about. What it talks about is that the angular velocity is simply 2 pi in radians over time of the frequency of oscillation. Or since frequency is 1 over period time is why this one will have a fraction when this one doesn't need one. So what does that mean? Well, if this speed isn't linear, it's going slow, fast, slow, speeding up, slowing down, speeding up, slowing down, we can get a waveform. This waveform can be described over here. If our x component, our motion component, is the amplitude times cosine, the angular velocity times time, if time is our x-axis, we'll see this motion. Well, if any of you have taken calculus, you can think of this as a derivative. The slope at this point is 0. So the derivative of position is velocity. So if the slope here is 0, we can just plot a point at 0. We know, let's say the slope here is a little bit down, let's call it -1, just like this is -1. The slope here is the max slope. This is when the ball would be in the center of its motion, if it was a pendulum. So that would be our max speed. Our velocity's amplitude would take place at the equilibrium position on the x graph. And then what's happened? Well, we see the slope is going down. It's still negative. It's still a negative slope, which is why this velocity is still in the negative area. But then the position graph is 0, so we put the slope of the position graph is at 0, so we put our point at 0. Well, what's the difference? How do we go from velocity to acceleration? Well, you can think of this like calculus again. We can take the derivative. Here we see that the maximum slope is going to occur right here, right here, right here, and right here. So if the maximum slope is occurring here, the amplitude of acceleration should also occur right there. Well, where did these maximum acceleration lines occur? Let's just take this line up all the way to position, and we see that the maximum acceleration occurs at the maximum displacement from this equilibrium position. When the ball, let's use the spring example, when the spring is the most compressed, the spring has the most force. Force is equal to mass times acceleration. The mass doesn't change. So the maximum force occurs when the spring is most compressed or when the pendulum is the farthest away from that equilibrium position. So the maximum acceleration occurs at the maximum displacement, but that's when the minimum velocity occurs. So going back to the equations, we can see that the displacement of x is equal, the velocity is negative angular velocity amplitude sine of tau theta, or tau time. So yeah, we have force is inversely proportional to x. That spring example, when the x is the maximum negative, the force is the maximum positive. Okay. These are pretty much, we just did these with calculus. So we have some equations that we can use to find omega. Omega is the point in radians through the oscillation the object is. Okay. So relating angular frequency and normal frequency. So we know that a ball on a spring, the mass on the spring, will complete one period over a certain time. Well, that time is going to be, if, say this is the position graph, if this is x position versus time, time is on the x-axis. We see that it's being pushed away, being brought closer, through the center, away from the spring, and pushed back. So this is one full back and forth motion. This can be described using the equations on this slide. So let's look at the energy. So if you've ever used a Nerf gun, you know that when the spring is very compressed with that ball, that's its maximum spring potential energy. When it's being released, it's losing spring potential energy and turning that spring potential energy into kinetic energy of the ball with mass moving. But energy wasn't destroyed, it simply moved. So as you can imagine, the spring being compressed has the maximum amount of spring potential energy, but additionally, when the spring is its most stretched, it has its max spring potential energy because it's going to want to bring that ball back like a slingshot. So you have max potential energy here, max potential energy here. It can only become kinetic energy. So right in the middle, we have max kinetic energy. Kinetic energy is the energy of motion. Again, the mass isn't changing. So you know you'll have your max velocity in the middle. You'll have your minimum velocity at either side. Should be a velocity of 0 for some infinitely small period of time. So what does this mean? Let's look at, here's a great slide that shows a pendulum and its identical situation as a spring. So here, just describing this photo, we have a pendulum past its equilibrium position, and we have a block past its equilibrium position. Now it has its maximum acceleration because it has its maximum force, and as it's going through its equilibrium position, gravity is not contributing to x motion, just like the spring isn't contributing to any x motion at this point. So it has all kinetic energy. But as it compresses again, like through at this point, it has its maximum potential energy, just like this does. So it will have its maximum acceleration in the other direction. So how do we use energy to solve for angular velocity? We can use this equation that velocity max is equal to the amplitude times the square root of the spring constant over mass. Spring constant, how hard is the spring to compress? If I have a truck suspension compressed a foot, that's going to be a lot harder than, say, a Nerf gun spring. And so it's going to be able to reach a higher velocity. So that's great that we know if a pendulum is swinging down, it has potential energy up here and kinetic energy down here. It's easy to calculate the potential energy, just this is some change in height and potential energy. It's all due to gravity, so there's mgh. The potential energy of a spring is 1/2 k, the k constant of the spring, times the amplitude squared. Amplitude, again, would just be the displacement from that 0 position. So when all the potential energy becomes kinetic, that's really easy. We just take the mass of the ball or the mass of the box, and both of these become kinetic energy, 1/2 mv squared. So that'd be very easy to solve for velocity. But what if it's somewhere in the middle? Well, just like a sled down a hill, when the sled is here, it has some potential energy, but it's moving, so it has some kinetic energy. So the sum of those two energies is going to be equal to the total energy. Here are just a couple practice problems. I'm not going to go over them. The steps are listed pretty clearly. Here we talked about where the forces come from, how the max force will come when you're at the max displacement of x in either direction. But the acceleration at any position, here we have max force. Here we have no force. How do we find something in the middle? Well, we can just use this equation. At some point in its motion, it is the square root of the k constant of the spring over mass. So here is a couple of practice problems to talk about. On the friction one, on part B, just remember that you do have your force of the spring in one direction, but you also have the force of friction. So the force total in this situation would just be the force of the spring minus the force of friction. Another one, so it just goes over acceleration. It does the steps pretty clearly. Great practice. Period equation. So how do you find the time it takes? So, little thought experiment. If I have a pendulum, two pendulums, this pendulum weighs 5 kilograms, this pendulum weighs 1 kilogram, and I stretch them back at the same exact angle. I let them go at the same time. It's the same length of string. Which one will take longer to get back to its first position? They actually take a different amount of time. Oh, sorry, this is for springs. For pendulums, we just have to change that K to an L, the length of string. Let me get back to that. Sorry, this is talking about springs. So for springs, the only things you need to know is the mass of the spring and the K value of the spring. Nothing else matters. So in that example, instead of pendulums, we can talk about two spring systems. If the springs are exactly the same and the 0 positions are exactly the same, but one box is being stretched back farther than the other one, this path of motion here versus this path of motion here, which will take longer. Well, if we look at our equation, we see that amplitude is shown nowhere in here, so it won't affect the period. All that matters is the mass and the K constant. So yeah, let's talk about here. We already know that through the 0 position of a horizontal spring, force is 0, net force is 0, and therefore we're at max velocity. If we have a hanging spring, wherever an equilibrium position is relative, right? If I put a small mass, it might only distend the spring this much. If I put on a much heavier mass, it might extend the spring this way, this much. And the equilibrium position is as described here, where the force of gravity is equal to the force of the spring. If gravity is pulling it down and the spring is pulling it up, it'll be the equilibrium position relative to the resting position of the spring. So the equilibrium position, even in a vertical, the maximum velocity is going to occur through that equilibrium position. So here is the same graph we shown earlier, it's just horizontal. See, we have the maximum forces occurring here, here, and here, and the maximum velocities occurring here and here through that equilibrium position. That's what this table describes. So it's pretty much all you need to know. You have your equations that describe each other. You have how to find angular velocity at any point. You have your time equation. Some practice problems. Feel free to work through them. Yep. If there's any questions, the next video will cover pendulums. And thank you for your time.